right, so there were lots of requests for problems to work on today. I'm going to get through as many as I can in the time that I have, which is an hour. So there were 3 problems from 2 different people. I'm just going to alternate them one after the other in the order that the people arranged them. So the first problem request was for homework 20, section 13.6, problem 3, which is we're told to use Stokes' theorem to evaluate f dot dr for f equal to y, z, x over the triangle given by that plane intersecting with x equals 0, y equals 0, and z equals 0. X plus y plus z equals 1 is my plane. Okay, so I started to write out kind of what we've got going on here, and it helps me to sketch stuff out. So I know that x, y, z equal 1 is a plane that has like normal vector 1, 1, 1. That's just something that we learned kind of early on in class about how to connect directions to planes and lines. So it's kind of pointing outward like this. Or I could think about that when I set y and z equal to 0, it means x is 1. Similarly, x and z equal to 0 gives me y is 1, and x and y equal to 0 gives me z is 1. And so when they said triangle, they meant that triangle right there would be where the plane sort of gets sliced by the coordinate planes right here. And I'm told it's traversed clockwise when seen from below. So kind of if I imagine that I'm right here and I'm looking up at the plane, then I would see things moving clockwise, which is that direction. From that perspective, like this looks like counterclockwise to me because personally I'm standing on this side of the plane. So that's how I reason through what direction they're talking about. And erase all my lines. Okay, so I just decided that the direction we're going is that direction. That would be clockwise when viewed from below. Okay, and I am trying to evaluate this line integral. And I'm told to use Stokes' theorem, but if I wasn't sure, I could remember that Stokes' theorem is for when I have line integrals over closed curves, which this is. And my Stokes' theorem is in my formula sheet right here. It tells me that the integral of c f dot dr is going to be the same as the surface integral of del cross f dot ds right there. So sorry, I keep moving the bar down there. So to solve this problem, I know that I'm going to need a normal vector to get my ds. And I also know that I'm going to have to compute that divergence. So I'm going to do the divergence first because it's just computation. It's kind of thinking about this maybe being a problem I get on an exam. It's an easy thing for me to finish. I have a really clear formula that I'm going to follow, and I don't think I'm going to like mess anything up terribly. So at the very least, if I didn't know how to do anything else, I could do this. Because I'm a little crunched for time, I'm not going to talk through the details of computing the divergence. Just, I take a component and do the determinant of the entries that don't line up with it. So I've got I hat d dy of x minus d dz of z minus j hat d dx of x minus d dz of y plus k hat times d dx of z minus d dy of y. And when I simplify, I've got I hat d dy of x is 0 and d dz of z is 1, so 0 minus 1, minus j hat d dx of x is 1, minus d dz of y is 0, plus k hat d dx of z is 0, minus d dy of y is 1. So I'm just doing all my partial derivatives. Partial derivative of y with respect to itself is 1, but partial derivative of y with respect to any other variable is 0 because it's a constant as far as those variables are concerned. So my divergence is just going to be minus 1, sorry, my curl is minus 1, minus 1, minus 1. So that's what I know that I'm going to put here in that surface integral I'm trying to evaluate. But I still don't know what to put in this dot ds, or what my bounds of integration should be. So I go back to my formula sheet. I need to find my normal vector ds, where ds is this thing. So I'll go ahead and sort of write that. So I just copy down those things for unit vector n. And before I said that my normal vector for my plane I could tell is 1, 1, 1, just from looking at this equation. And so to make that a unit vector, I just divide by the magnitude, square root 1 squared plus 1 squared plus 1 squared, or just 1, 1, 1 over root 3. If I didn't remember how to get my normal vector from a plane like this, my other option is to take the surface I was given, solve for z in terms of x and y, and then use my normal formula. N is, where do I put the negatives? Negatives on the f's, so minus fx minus fy 1. And so I'm going to get negative 1 for the derivative with respect to x, so 1. Negative 1 for the derivative with respect to y, again 1, and then 1. So two different approaches, same answer. And I anyhow needed to compute these derivatives to calculate my ds, which is square root 1 plus fx squared plus fy squared, which is square root 1 plus 1 plus 1, or root 3. So my surface integral is going to be negative 1, negative 1, negative 1, dotted with 1, 1, 1 over root 3 times root 3 dA. And the area that I integrate over is the shadow that my surface casts. So that's going to be in dy dx. And to figure out those bounds, I just kind of think about that drawing I had of my plane. That shadow is sort of enclosed by this line that goes from y equal 1, x equals 0 to x equals 1, y equals 0. So I want to be integrating over this area right here. So I wrote dy first, so y is bounded below by 0 and above by this line. So my lower bound is definitely 0, and I have to figure out what to put here. A lot of people are going to want to just put 1 because my highest value of y is 1. But remember, that would be like a rectangle shape, bounded above by 1 everywhere. I actually want to put the curve that's limiting me. This line right here doesn't always hit 1. Sometimes it hits different values. And I could do some like point slope stuff to figure out that that line is y equal 1 minus x. So my upper bound is actually 1 minus x. And then below that, those y bounds, I just figure out where x goes. X is bounded below by 0, and it goes up to 1. So I have those bounds right there. So then I could evaluate my dot product, just component-wise, multiply together and then add. So minus 1 times minus 1 is minus 1 times 1 plus minus 1 times 1 plus minus 1 times 1. And those two root 3's are going to cancel each other out. And I'm just left with my dy dx here. Or minus 3, the integral from 0 to 1, 0 to 1 minus x dy dx. And I'm not going to evaluate this integral. I am going to note that an integral with nothing inside is like an area or volume. A double integral dA is area, triple integral dV is volume. So I actually could just do minus 3 times area for the area of this triangle right here. That's a little faster for me. It's minus 3 times 1/2 base times height, but the base and height of that triangle was just 1. And if I evaluated this double integral, I would hope to get the same answer. Sorry to go through that last part kind of fast, but I'm trying to get to lots of problems today. So the second person requested for their first problem, one of problems 1 through 4 from this assignment, whichever one is most relevant to the exam. I'm not going to tell you that, so I'm just going to pick randomly. I'm rolling a d4. We're doing problem 1. So we are finding the way to set up the triple integral for a sphere with radius 5. Okay. In Cartesian, cylindrical, and spherical coordinates. All right. So a sphere with radius 5, to do this problem, I'm going to have to remember that that's given by this equation. X squared plus y squared plus z squared equals 5 squared. And I'll try drawing my sphere, I guess. I'm not so good at them. It just looks kind of like a circle, but it's got radius 5 here. I'm going to take this picture and think about it moving forward. So my Cartesian coordinates are going to be in was there a thing inside that I have to convert? Oh no, I just have a space to indicate like what is dV. Okay, so it's going to be dz, dy, dx. I get to pick whatever order I set things up in general. WebWork told me it has to be dx, dy, dz, so I guess I'm going to do that instead. Okay. So my x has to go on my innermost bounds. Oops. And it's the variable that is allowed to be in terms of y and z. So I just go to my surface and I solve for x. X squared is 25 minus z squared minus y squared, or x is plus or minus root 25 minus z is z squared minus y squared. So the positive branch is the top part of my sphere, and the negative branch is the bottom part of my sphere, like below the xy plane. But this tells me my upper and lower bounds for x, minus root 25 minus z squared minus y squared, positive root 25 minus z squared minus y squared. Then to get my y bounds, two different things I can do. I can kind of look at the widest shadow my shape casts. I would normally do it in the YZ plane like I drew, or the XY plane like I drew here. But because I'm doing it in Y and Z, I would actually draw it. It's kind of hard to show because it looks kind of like that. But that's the slice of the sphere that lays in the YZ coordinate plane. So I can figure out what that shape is. It's a circle with radius 5 in Y and Z. So it's y squared plus z squared is 25. And I can use that to solve my y bounds. Or if I'm ever in doubt about what to do, after I've got my first bounds, when I'm moving out, all I do is set my upper and lower bounds equal and see what happens. So this approach right here would give me that y is root 25 minus, I am so used to writing x, z squared. And it has positive or negative branches. Or setting my previous bounds equal, I've got root 25 minus c squared minus y squared is equal to negative root 25 minus c squared minus y squared. At this point, I would notice that the only time a positive and negative number are the same are when that number is 0. Like plus minus 1 can't be equal, so it must be that there's just a 0 here, then positive and negative don't matter anymore. Or I'm solving for 25 minus z squared minus y squared is equal to 0. Then that's going to get me to the point of having y squared is 25 minus z squared, which again gets me that plus minus root 25 minus z squared. Okay. Because z is outside y, it's allowed to be in my bounds for y, and I see it here, but I don't see x, which isn't allowed because it came before. So things are looking good so far. I haven't messed up the order that my integral is allowed to be set up. And then for my last bounds in z, I could just look at my picture I drew and see that the circle with radius 5 must be bounded below by minus 5 and above by 5 because that's the radius. Or if in doubt, I set my two bounds equal. Root 25 minus z squared is equal to minus root 25 minus z squared. That gives me that 25 minus z squared has to be 0 because of that previous argument that positive and negative numbers are never equal unless that number is 0. And so that just gives me that z is plus or minus root 25 or plus or minus 5. And that would be my answer for the first set of boxes, with p here just being 1, because when I do dx, dy, dz, when I do my Cartesian coordinates, I don't need something here to account for the dv. Then next, I'm asked to try it in cylindrical coordinates. So I'm actually going to copy paste my Cartesian first, because cylindrical is kind of like halfway from Cartesian to spherical. Okay, sorry about that. I'm trying really hard to copy paste on my tablet and it is not working. Luckily, you all are not seeing the part where I'm copy pasting notes from my tabletop group. I'm leaving it there instead of deleting because I'm short for time though, so you all are gonna see that later, I guess. Okay, I should have gotten it now. Cool. The tabletop notes were, they need to recuperate here for some time. So I copy pasted my Cartesian coordinates, and I'm trying to convert to cylindrical. Cylindrical are coordinates that have dz, dr, and d theta. And the specific order that I'm supposed to do this one in is exactly that order. I'm just copying that down right now. And they're like polar coordinates. My dA is r dr d theta, or my dv is r dr d theta dz. So I do need an r in here. I'm actually going to move it over a little bit. But z is the same as before. Like z is still a variable, so I could go ahead and use the same types of bounds I would get like this. From if I just started at my sphere equation, x squared plus y squared plus z squared is 25, and then solved for z. The only issue is that x and y aren't variables anymore. Instead, I want to be in terms of r and theta, so I do need to remember that x squared plus y squared is r squared in polar coordinates. And that is the kind of thing that would be on your formula sheet right here. So instead of 25 minus x squared minus y squared, I actually just have 25 minus r squared. 25 minus r squared. And then r is like my radius in the xy plane. The sphere has radius 5, so I know that r goes from 0 to 5. And I'm covering like the whole sphere, like I take a whole circle whenever I take a slice of the sphere. So I know that my theta goes from 0 to 2 pi. I rotate all the way around the like xy plane when I'm covering my sphere. If I didn't know that my radius was 0 to 5, I could solve it setting these two equal with that same plus minus argument. I would end up, I'm just drawing my circle. Imagine it's symmetrical. I would still get my 25 minus r squared equals minus 25 minus r squared gives me 25 minus r squared is 0. R would be plus or minus 5, but radius is always positive, so it's bounded below by 0, goes up to 5. But I'm going to need to like visualize this and know what theta means in order to get the theta bounds, so it's just as easy to do it from the picture. In the xy plane, my sphere has radius 5, so that's where I get my 5 from, and then I have a whole circle, so I need all 2 pi of my radians to cover the whole circle. And those would be my cylindrical coordinates. And then lastly is spherical. I'm not going to copy paste because it is no longer helpful to me. And the thing I have to remember is this rho squared sine phi that is needed for dv whenever I use spherical coordinates. So that's what's being asked for in this box. Just what do you put inside a spherical integral? And then I'm told to do it in order d rho, d theta, d phi. These are all going to be constant numbers, so it actually doesn't matter for this particular shape. Rho is my radius. I guess I'll just draw a few different versions. So rho is my radius starting from the origin out. My sphere doesn't have a hollow part to it, so I start from 0. And my sphere has radius 5, so I go out 5. And then for my theta, doing the same thing I normally do. That's a cross section of my sphere. That's the part of it that lives in the I did this kind of the opposite order you're usually used to. Sorry about that. That's going to be the cross section that lives here in the xy plane. Just like before, it goes all the way around. Theta is the same between cylindrical and spherical coordinates. So it's 0 to 2 pi. And then for phi, I'm thinking about kind of the angle that I sweep from my xz when I'm drawing my slice of a sphere. So here's like a little orange wedge of a sphere, and then when I spin this around 2 pi, that's the angle we just talked about. That would cover the entire sphere. And so for phi, I'm just wondering about this angle, starting from the positive z-axis, being 0. There's no empty part there, so I do start there. And then just how far do I swing down to make my shape? I go down a full pi. So for this problem of the three, I think that the spherical coordinate is the hardest. This object is best for spherical coordinates. It's just that you do have to conceptualize like what spherical coordinates are. So we're about 25 minutes in. I'm going to try to pick up the pace a little. The next problem I was asked to do was this homework 2013.6 problem 4. Use Stokes' theorem to change del cross f dot n ds to an equivalent surface integral. Oh, I see. Okay. I'm writing that down. Where f is given by x, y squared, x, y, z. N is the unit upward normal, and s is the part of the paraboloid z equals 4 minus x squared minus y squared. So I'm just copying all that down. Okay. So S is this like upside down bowl that has height 4, and then goes down to a circle in the xy plane with radius 2. The way I would see this is when x equals 0, y equals 0, I'm going to get z equals 4. So that's how I know my height is 4. And then when z equals 0, because I'm told that the bowl intersects z greater than or equal to 0 is the only z I consider. So I think about where z equals 0, that's where my surface ends. Then I get 0 equals 4 minus x squared minus y squared, or x squared plus y squared is 2 squared. That's how I knew there was this circle down here with radius 2. Okay, so what is this problem asking me to do? They say I'm trying to calculate this integral. My surface is that bowl shape with a unit upward normal vector. So given this z, I could calculate that fx, fy normal vector and compute the curl and evaluate everything. Or I could convert it to a line integral. Normally we go the opposite direction because line integrals are kind of hard, but for the upward oriented object, it has this line integral right here, like as its lower bound, that's the edge of my surface. And thinking about the fact that like right here, that upward oriented vector that's normal everywhere on the surface would kind of slowly rotate to be facing towards the screen right now. I know that the orientation of this curve by the right-hand rule would be in this direction. Just kind of like imagine putting your hand so your thumb is pointing out of the curve. Sorry. Then my palm has to open up in the direction of the arrow I drew right here. So if I was interested in parameterizing a circle, I could convert this del cross f problem into a line integral. I would do my r prime here, plug in r to f. That would be fine. But they're telling me the bowl shape I'm thinking about that has that edge shares an edge with this disc shape that's way easier to think about. So instead, what I want to do is evaluate my surface integral x, y, z just here. Okay, I've got that curve, I've got radius 2, and everywhere this normal vector is just k hat, 0, 0, 1. Because this surface is flat. So already this is an easier problem because I don't care about two components of my curl. And also on this surface, z is 0 because I live in the xy plane. So my f becomes x y squared 0, and my n becomes 0, 0, 1. And this is a much easier thing to calculate than the bowl shape that would require a funny normal vector, 3 components of f, etc. So I'm going to calculate my curl, I guess. I hat, j hat, k hat, d dx, d dy, d dz, x y squared 0. But what I'm going to note is my normal vector is 0, 0, 1. When I dot that with my curl, that means that whatever the x component is going to go away. Whatever the y component is going to go away. And I really only care about my k hat component. So I've got something I hat plus something j hat. I guess minus something j hat if you want to be real particular about it. Those aren't ever going to affect my problem. I only care about k hat times d dx of y squared minus d dy of x. And that happens to be 0. I'll use something different because it would be different. That's my curl. I'm not even going to bother with the other components. Then del cross f dot n, the thing I anticipate integrating is whatever those first 2 components were 0, dotted with 0, 0, 1. That's going to give me 0 times star is 0, plus 0 times squiggly shape is 0, plus 0 times 1 is also 0. So del cross f dot n is 0. That means this integral that I was trying to set up here is just 0. Integral 0 ds. And if I wanted to set up the bounds, it would be like over a circle. You could pick whatever type of bounds you want. The one that normally occurs to you would be to do Cartesian, like I said it's radius 2, right? Yeah. Minus 2 to 2 root 4 minus x squared root 4 minus x squared 0 dy dx, or polar coordinates 0 to 2 pi, 0 to 2, 0 r dr d theta, just to give you an idea of how you would do this problem, but I'm pretty sure the answer is just 0, and I'm gonna hope that's right because otherwise I messed up something in this problem. Cool. Great. I was nervous. This is such a long video. I didn't want to have to go back and do something. So yeah, if you did this really complicated integral to start, the way it's given, you would also get to 0 someday, but it would involve like calculating the normal vector for the surface, plugging in this quantity for z, taking the curl of this f, where you don't know that you get to skip 2 components, and then setting up an integral and evaluating it over a circle. So this is just like a neat thing you can observe that saves you a lot of time. So it's a cool problem. I like it. It did kind of trip me up at first when I was reading it, even though, because it says change this to an equivalent surface integral. Just remember, Stokes' theorem is for changing a surface integral into a line integral, but it doesn't like constrain you to stopping at that point. You can then change that line integral into an easier surface integral. You could actually draw any funny shape you want for your surface, and as long as it shares that base, it keeps erasing things, it's still going to have the surface integral is 0. So it's a really cool Stokes theorem fact. I'm glad we got to work on this problem. Moving on, the second problem requested from the second person was homework 1813-2, problem 4. For this problem, we're given the vector field f equal to e to minus y I hat minus x e to minus y j hat. We're told it's conservative and to find a scalar potential f to evaluate the line integral over any smooth path connecting these points, 0, 0 to 1, 1. So this is a fundamental theorem of calculus for line integrals problem where we know integral f dot dr is f of b minus f of a if f is like the gradient of some potential function. We can use this property for like not closed curves, and it helps us not have to parameterize a curve, which is kind of nice. Evaluating line integrals is personally my least favorite integral we learned, so anytime I can find a different way to do it, I'm pretty happy. You can also use it for closed curves, but at that point your starting point and end point are the same, so you always get 0, like the answer we just did. But in order to use this property, we do need to be able to find that potential function. So we remember that gradients are like df dx, df dy. So that means that this component of f, the x component, is the derivative of some function with respect to x. And then this component is the derivative of some function with respect to y. And we just integrate those components to try and uncover the function that generates that gradient. So I integrate my first component, e to minus y with respect to x. And my second component, minus x e to minus y with respect to y. So when I evaluate this first integral, e to minus y is a constant as far as x is concerned. So it's actually just integral of e to minus y dx. That's x e to minus y. And so it's possible that my function is x e to minus y, except for there could also be some constant that depends on y. It's a constant as far as x is concerned, but it's allowed to have terms of y in it. That would also give me that e to minus y is the derivative with respect to x. That's why I go over to my second component and I try integrating that one with respect to y. That way I can uncover any y terms that I missed before. When I integrate this function with respect to y, minus x is a constant as far as y is concerned. And then the integral of an exponential is like divide by the constant inside, but the exponential stays. So it's 1 over minus 1 e to minus y. kind of like e to 2x when you integrate it is going to give you 1/2 e to 2x. I'm using that same rule except for my number is -1. And that gives me x e to -y, which is the same thing I found before here. And so I would actually just like throw away any new functions I find, and then anything that's left over, I would throw away any functions I find that I already had before, and then any new ones that are left over become that c. In this case, there were no new functions, so I've like determined that c of y is 0, and I can just cross it out. But I don't double count my x e to -y because I previously found that function. If I had more time, I would show you how given f equal x e to -y, I could compute grad f and get e to -y minus x e to -y. And if you're like still feeling iffy about why we sometimes keep terms and sometimes throw away terms from our second integral, doing this, like calculating the gradient from the function and sort of reconnecting it to the start of the problem, is a really great way to see where the double of x e to -y comes from. But in this case, that's just my function because I don't have a lot of time. And then I can evaluate this line integral that I'm given by just evaluating the function at those 2 points, 1, 1, and 0, 0. So my integral c f dot dr is going to be f of the second point, 1, 1, minus f of the initial point, 0, 0. So that's going to be 1 e to -1 minus 0 e to 0. Or just e to -1. I guess we could see if I got that right. Cool. And I'm not going to type that f in there, but it would be that x e to -y I found before. Okay, on to the fifth problem, or the third that the first person requested. We are given that S is the hemisphere, x squared plus y squared plus z squared equals 4 for z greater than or equal to 0. So I'm looking at the top half of a sphere, and I want to evaluate the surface integral, z squared ds. Okay, so I'm going to draw it out. And it is 4, so it's 2 squared. Oh, okay, hold on, put that back. Oops, okay. So I've got my 2 squared there. So my sphere is going to go like 2 here, 2 here, 2 here. And I'm only thinking about the positive part for z greater than 0. I'm going to start setting this up in Cartesian coordinates. I imagine at some point I'm going to switch to something easier to evaluate. But for now, let's go with the thing that like matches like how I want to set up all my formulas. So this is a surface integral. I guess what's kind of confusing to me is that this isn't how I expect to see a surface integral. I'm going to assume that they were kind enough to do f dot n for me in advance, I guess. So that's cool. And I'm just going to go get my formula for ds. where my surface is this sphere, so it's square root 4 minus x squared minus y squared. So that's my f. My f sub x then is minus 2x times 1/2 4 minus x squared minus y squared to the minus 1/2. So I did like a power rule on 4 minus x squared minus y squared to the 1/2 power, and then a chain rule because I had a x squared function inside. So that's just going to give me x over square root 4 minus x squared minus y squared. Fy is going to be the same, 2y, actually minus 2y half 4 minus x squared minus y squared to minus 1/2 y over root 4 minus x squared minus y squared. So 1 plus fx squared plus fy squared is going to be root 4 minus x squared minus y squared. Nope, sorry. 4 minus x squared minus y squared over 4 minus x squared minus y squared plus x squared over 4 minus x squared minus y squared. I just squared this thing. Plus y squared over 4 minus x squared minus y squared. Then I'm going to get 4 minus x squared minus y squared plus x squared plus y squared over 4 minus x squared minus y squared, just adding fractions together. So that's going to be 4 over 4 minus x squared minus y squared. Then I wanted the square root of that. So that's 2 over root 4 minus x squared minus y squared. So cool, I've got that. Figure out what goes on those bounds in a second. So I have, oh man, I wrote that wrong to start. Sorry everyone. It was ds is that quantity, dA, I left it off. So then I've got dA right there. And so I can replace my ds with 2 over root 4 minus x squared minus y squared dA. And then I had z squared here before, but I'm converting this into an integral over an area, specifically this area down here. So I can't have it have z in it. Instead, I need to replace z with the function of my surface. So that's just z is this root 4 minus x squared minus y squared, or z squared is 4 minus x squared minus y squared. Simplifying things, I can bring my 2 outside. I'm going to have some bounds that I haven't decided what they are yet. And then 4 minus x squared minus y squared divided by square root of that is just going to leave behind a root 4 minus x squared minus y squared dA. That seems like a really hard thing to integrate. I'm going to be integrating over this circle shape that my surface casts as a shadow in the xy plane. And I know that x squared, y squared terms get simpler when I switch to polar coordinates. So I get to pick whatever dA I want. At this point, I'm going to convert to polar. I needed to do Cartesian for like all my derivatives to be easy, but now I can pick any coordinates I want to evaluate my integral, and I'm going to pick polar coordinates. Like in a problem we did earlier, x squared plus y squared is r squared, which means minus x squared minus y squared is minus r squared. So I'm actually looking at 4 minus r squared, r dr d theta. And then to set up the bounds over this circle shape, I know the radius of my sphere is 2. So the r is 0 to 2 because it's like not hollow inside. And then my theta, when I'm spinning this way, maybe do it in a different pen color, this way, my theta starts at 0 and goes to 2 pi. I have the entire circle is showing up, not just a part of it. And so that is the integral that I would evaluate. I'm not going to work through the whole thing because I only have 10 minutes left and I want to get to that other problem. But to finish out this problem, you need u sub. You do u is 4 minus r squared. Then du is minus 2r dr. Or I can replace r dr with du over minus 2. So this becomes square root u du over minus 2. And to make it easier for you as you continue the rest of the problem, I'll go ahead and change the bounds. You could choose not to change the bounds and just do the substitution at the end. U is 4 minus r squared. My 0 becomes 4. And my 2 becomes 0. This integral is like backwards, so I can swap the bounds back with a negative. And kind of the minus 2 down here is going to cancel with that minus and 2. And I will get just integral 0 to 2 pi, 0 to 4 square root u du. And at this point, don't swap back the variables when you're done. If you're happy doing a u sub, just from this point, integrate and then sub in later if you want. And now with 7 minutes, we're going to get to this very last problem. The third problem requested by the second requester. Given this integral that I better copy down because it's super long, we're looking at homework 12, 12.5 problem 4, and we're given a triple integral. A weird one though. dz, dy, dx. We're asked to swap it to dy, dx, dz. Okay. And the f doesn't matter. We're not actually going to evaluate this one. So to swap order of integration, like with most things, I want to draw what's happening first. Z, x, y. Root 4 minus x squared, like this is a z bound, so it's z equals that. So I'm bounded below by z equals 0. That's cool. I didn't draw lower than that before. But then I'm bounded above by this shape that would actually like go on forever. It's like a tunnel, I guess, like a piece of paper folded over. I'm gonna leave it like that for now though. And then in y, sort of my second bounds are y, so I can do y equals that. I'm bounded below by Actually, you know what? I will leave my weird sheet thing up for a little bit. So I'm bounded below by y equals 0, so the part of the tunnel that would stretch past the xz plane, that doesn't get to happen because y is negative there. And then y only goes up to this shape. Sort of the tunnel that you'd have going this way, part of a cylinder, I guess, of y equals root 4 minus x squared. So I'm going to draw these pieces so they're touching where they would. Okay, and there's my negative x. But then I'm also told that x is bounded below by 0, so all this stuff actually doesn't get to happen. And instead, I kind of start there at 0, and I go out to x equals 2. I want you to know I'm not like drawing that out further. I'm just, it still cuts off here. It just kind of looks the same as before. Okay. So this is the curve y equals root 4 minus x squared, or it's part of a circle with radius 2. So it's up to 2 there, 2 there. This is part of the circle z equals root 4 minus x squared. So it's a circle in the xz plane with radius 2. So it goes up to there. So I've basically created like not quite a sphere, I don't think, because it's not sphere shaped like up in the z part. Honestly, this shape is hard for me to visualize, but that's okay. I don't need to do better than this. This is such a weird one to do. Okay. So now I'm going to try to do my switching the coordinates to y, x, z. Before, my bounds for y were 0 to root 4 minus x squared. Technically, that's still allowed because y comes before x, so x can be in the bounds. And if I look at my shape, maybe a version of it where I didn't draw all over it, x, y, z, circle shape, and you just kind of like keep going that way. Weird. Okay. When I look in y bounds, I do go from 0 up to that curve, so I can keep it. Then my x bounds before were 0 to 2. There's nothing wrong with that because you can always have constant number bounds. It's not going to hurt anything. But then if I did that, my z bounds would be 0 to root 4 minus x squared, like if I just put everything in the new order. And this is where I have a problem because z happened after x, so it can't have x in it. In fact, because it's on the outside, it has to be only numbers. So my issue becomes trying to write my z bounds not in terms of x. So I'm just going to look at the zx part of my surface now, which is way easier. It's like that. And my x, I want to do first. It's the thing that's going to depend on the curve. It's still bounded below by 0, so that's okay. But then it goes out to this curve, z equals root 4 minus x squared. That's like the furthest over to the left it can go, because I drew it kind of backwards. We always think left to right for x bounds. This is right when x, y are facing the normal direction. Anyhow, so this is the same as x is equal to root 4 minus z squared, because we've got z squared is 4 minus x squared, so x squared is 4 minus z squared, or x is root 4 minus z squared. And then dz, my final bounds, I could look at my picture. Like before, I said it goes up to height 2, so z is between 0 and 2. The furthest up my shape goes is up to 2. Or if I didn't have that visualization in my head, I could just say I set my prior bounds equal and see what happens. In that case, I would get 0 is root 4 minus z squared, or 4 minus z squared is 0, or z is root 4 is plus or minus 2. That's where the 2 comes from. I would have to remember that z is bounded below by 0 to know that negative 2 can't possibly go here. So that's why I start from 0 and go up to only the positive 2. This one was so weird with like half of it not changing. So I just want to make sure it was right before I like declare victory over it. Nope, that's actually the 0. Sorry, I'm used to having to do like parentheses for stuff. And then my f of z, g of z was, f is the bottom, 0, root 4 minus z squared. Let's see what happens. No, not correct. What happened? Oh, a was my lower bound 0, b was the upper 2. That's my bad. Okay, so that was correct. I thought when I started writing it down that they were going to give me a harder problem of like trying to convert y to something that includes z. But our z shape was so simple before, it only depended on x, that swapping that one out of order didn't change anything. So that's why this worked. Only like 2 minutes over an hour. I'm feeling really good about that. We got 6 problems done. Some of them may be a little faster than I would have liked, but hopefully this helped. Good luck on your homework and good luck studying, and I will get this posted.